Okay. Last week I was on PTO and I just started work in reviewing Renan's PR to bring the support of ASOC to Crimson, and I think I will finish reviewing Chunmei's PR for adding the alienized blue store. But Chunmei, I think probably you could amend the commit message with the details and the strategy of your change. That'll be very helpful. And
I'm rebuilding the code now.
Again, sorry.
I'm rebasing the code and the code now.
Thank you. And that's me. I'm Nam. How's it going?
1 second before we continue, Kifu.
Yes.
Is there? I would like to suggest. I only this morning here, and I only had 10 minutes to read Sam's document, the new design document. Is it a good idea to spend half an hour of this meeting just for Sam to present the design?
Definitely. If
that's what I figured I'd do. I don't think it's going to take half an hour either. It's a little simpler.
Sorry, I didn't hear you.
Yeah, I think that's a good idea. We'll do it after, or maybe at the end.
Be good. Thanks.
And I'm Nam.
Yeah. So for me, same as last week, I have been working on CBT. I'm actually at the debugging stage right now. Just figuring some stuff out, really close to finishing being able to present the CPU cycles per operation. Then I'll make a pull request. I mean, currently it's on my fork. I'm just fixing some problems, and after that, I will continue working with Radek closely to see how we can improve it even further, or what we can add to CBT even more, so it'll be better for us. That's pretty much for me.
Thanks, and Chunmei.
Last time I said there are some memory assert. So I think it is because the Alien Blue Star used the Ceph logger, and so I have to disable it in the Alien Blue Star because we didn't initialize any logger, any Ceph logger in the Ceph context CCT. So I have to disable that logger in the Alien Blue Star, and then I rebase the code. I made some compare error when I used the Ceph aerator. So I have asked the redact to help me to solve that problem. So still has a little problem about the compare. And then I think I can do the release version testing.
What do you mean by compare?
When I use the Ceph aerator, so there's some compare error. I don't know because I didn't really understand the Ceph aerator currently. I just read the code, and there's some used deleted constructor. So that one has helped fixed by redact. Redact has told me how to fix it, and they still has some build error when I use the do with with the Ceph aerator. So still has some build error. So after, I think if it is the build error is fixed, then I think maybe the release version will work because the memory assert, I think I have solved it.
Okay, thank you. Redact.
Hello, I'm still on PTO, so working in a kind of tourist mode here.
Okay.
I've I'm guiding, first of all, I'm guiding Avnum in the CBT SeaStor op metric, and also I pushed a new series of patches for SeaStor. Rework according to Avi's comments. Also added some new comments there.
So I didn't notice
Apart
that you
from
have a
that,
guest mode after your name.
yeah. Apart from that, I need to backport non-crimson change. I need to backport the zeroization, the fib zeroization to Nautilus. That's all.
Thank you. And Ronan.
Hi, everybody. I have redone a version of the ASOC code according to what we discussed last week, according to Sam's suggestion, and hopefully I will deliver it today. I also added the better shutdown code, and so all of this is working. If I get the comments right, I'll deliver everything today, including the format, the Clang format script I used for these files. So if anybody will want to tweak a Clang format file, it will be a part of the comment message. And other than that, I'm reading and trying to learn things related to SeaStor and now this document. So that's me for week.
I'm also reviewing your change this morning. Okay.
So better wait
Sorry.
for the next version. Better wait for the next version.
Okay, cool. Okay.
Yep, I'll have a look at it in the morning.
Yeah, hopefully
Once you push it,
I'll do it today. Sorry?
I said I'll take a look tomorrow morning or whenever you push it.
Good, thanks. And thanks in advance.
Sam.
Do you want to do things in first? That way I can just segue right into the document. Do we want to do Ying's in first? That way I can just segue directly into the document.
Sure. Yingxing?
I was studying BlueStar algorithms and Flash and try to understand the SeaStor background and plan last week. I think that's all.
Sam, I think it's all yours.
For Crimson, at least, I've been mostly working on the SeaStor design doc. I did have a quick question. Well, I guess I'll talk about that at the end. Let me see if I can get this shared. Hapsec. No, I can't. Can you guys follow in the document, or do I need to find a way to do screen sharing?
I can follow.
We can follow, I think, yeah.
Okay, so this won't take super long because the overall concept is pretty high level at this point. But the right sort of design guideline to think of here is Btrfs on a log structured file system. So if you know anything about Btrfs, it uses essentially a wandering tree sort of deal with a single superblock it periodically writes out so you can find the root. But it does not attempt to do the log structured thing where it always cleans a segment before it writes back to it. So we're going to make a few changes so that we are able to do that part efficiently. But other than that, the overall design should look at least a little bit like Btrfs. It clearly doesn't share any structures with Btrfs as we are not implementing a file system, and there are a lot of things we don't need to do. But the overall tree structure is analogous, I think. Who just joined? XHD? No, anyway. Welcome. Okay, so the first part is just some details about the physical layout on disk. I think this shouldn't be terribly surprising. The goal here is twofold. One, we want to be able to physically read the disk and interpret which things are data blocks versus which things are metadata, right? Just at a course level. So and I made a few choices for terminology. Rather than talking about segments or zones, I'm talking about streams. but for streams, you can definitely read zone if you want. That's fine. Blocks mean aligned or 4K
A question?
aligned. Go ahead.
A question. Why do you foresee only 2 streams for SSDs of the NVMEs?
Sorry.
You mentioned that you envision two streams only for.
Okay, so the very next
SSDs.
sentence is that the exact number is a tuning parameter, and I'm not really making predictions here.
Yeah, I understand, but I'm trying to see.
Right.
We're trying
So
to understand
my point here is that it's not necessarily just 2, and this is per shard, by the way. So if we have, let's say, 32 cores on a disk, that would mean 64 streams open, 2 per shard. But I really want to emphasize, I am not putting a flag in the ground about this. The goal, all I'm trying to point out is that there are at least 2 different regimes: a disk where we probably don't want more than 1, and SSDs where more than 1 is probably fine. And depending on exactly how many streams we can productively have open, we will make different choices. So the metadata layout needs to be generally flexible enough to permit writing to more than 1 stream at once. Does that make sense?
Okay, thanks. Yeah. Thanks.
I'm trying to be I'm specifically trying not to introduce details of the physical structure of the disk beyond the assumptions we actually care about, which is sequential access, pretty much, and that reads are generally cheaper than writes.
But Sam, probably regarding to the number of stream, I still have a question.
Sure.
Because it would be ideal if we can use different stream for different kind of metadata change because they don't share the same life cycles.
Yeah, that's precisely why I want to be able. That's precisely and exactly why I want to be able to have multiple streams.
Okay.
It's not that we have, but I also don't want to have to. Does that make sense? I don't want to make it mandatory.
Yes, we can interleave different kind of metadata changes into a single stream, but it's not optimal. But I'm
going to point out the following things that are maybe not super obvious. For a single shard, and for the rest of this conversation, we'll just talk about a single reactor, right? So for a single core, all operations are serial, right? And we're not going to make statements about what things transactions can span. So all transaction deltas have to live in a single stream. I'll let that settle for a bit. But it does not follow that every block has to be in the same stream. So I'll come back to that in just a bit. So a stream will be probably designated the journal stream for each core, but we will be able to write out blocks to other streams as well.
If I understand correctly, what it means that if a transaction should only write to a single stream instead of together different changes to different streams, just because they belong to different trees.
No, it's because when we read back the journal, we need to read back a sequence of deltas in an order. If we write them to different streams, we can't necessarily do that. Or we can, but it's not logically different. You'd have to include sequence numbers, so it would be serialized anyway. It wouldn't be any faster. There's another reason, too. We want to be able to garbage collect journal segments all at once. Because journal deltas are going to all go out of scope all at the same time. And I'll talk about that a little bit more when we talk about the difference between deltas and blocks.
Okay.
So the way I see it is this. The sort of logical, everything that we think of as a file system, the data blocks, the extent blocks, the indirection blocks inside of a B tree, all that stuff, those are data blocks. They're 4K aligned chunks of disk space that are a multiple of 4K in size. That shouldn't be that surprising, right? Most file systems work that way. You don't allow unaligned chunks of data. By contrast, deltas are what we would normally consider in a file system to be a journal. And this part is sort of a departure from Btrfs. As far as I know, Btrfs doesn't work exactly like this. I like this design because it makes it easy to overlay different internal structures. I'll talk about that a bit more in a bit. But the idea is that if we want to write out a transaction that changes the allocation tree let's say we want to write out a transaction that creates an object. What do we have to touch? We have to actually create a new block containing the data for that object. Let's say it's like a 2K object, right? We need to create the O node. We need to create the entry in the O node table that maps the H object to that O node. And we need to create an entry in the allocation table that tells us where it is. Or more accurately, that makes garbage collection fast. So all of those different updates need to all land in the same data block and get written at the same time, because they have to happen atomically. During recovery, we have to recover either all of them or none of them. Does that make sense? It's why journals are always written to a contiguous segment of disk.
I kind of agree with you that it's essential to use a single monotonically increasing sequence number for a transaction.
No, it's more than that. So when you do the write, the way this is typically handled in a file system journal, or BlueStor for that matter, if you go look at RuxDB, is what you do is the journal agent inside of the file system or storage system writes to a declared contiguous portion of disk and then writes a checksum at the end. When you're doing recovery, you read journal segments until you find something that doesn't checksum right. And that's when you know you've reached the end of the journal. That way, either every journal transaction you read is either all there or you completely ignore the whole thing. You never apply part of a transaction. That's just sort of basic storage stuff. So in this design, that unit is a record containing all of the deltas that comprise the transaction and any blocks that you want to include. Optionally, you may have chosen to write out blocks to another stream prior to this commit, but those blocks won't be committed until you commit the deltas that link them into the tree. So if you did have blocks, okay.
So this is the part I wasn't sure I understand. What you're saying, if the transaction involves blocks elsewhere, you wait for them to be written.
So okay, it's like this. So this isn't going to be true so often when we're doing a write to an object, but let's say we're garbage collecting or we're relocating a block because we're cleaning a segment, right? So we have some information about the age of that block. We know it's been around for like 2 weeks. So if that's true, we definitely don't want to include it in the journal stream if we don't have to, because odds are it's going to live forever, right? So if our storage layout, or if our storage device makes this a good idea, then what we would do instead is we would write it to a secondary stream, into a record that isn't a transaction. It's just a new record with no deltas in it. Then, in order to commit the change, we write a second record into the journal stream that records the change to the allocation tree and the parent block.
Okay, that's the part I wasn't sure about. You already written a block to a different stream, and now it's there. Currently there is a problem,
all we've done at that point is bump the write pointer on that stream. That block doesn't really exist yet. It doesn't exist.
It's not allocated yet, right?
It's more like it's forward allocated. Different file systems have different terminology. It's definitely free. We definitely wrote a block that is available for writing, right? We haven't overwritten anything, but we haven't updated the tree so that it can actually be found. So that part's what the transaction that commits is. So to do that, we need to update the leaf in the allocation tree where the old block used to be. We need to update the leaf in the allocation tree where the new block is now. We also need to update its parent pointer, let's say in the extent tree for a particular O node. So those three changes all have to be written atomically for the move to be atomic, right? Otherwise, we could end up with 2 pointers in the same place, or a block that is part of the tree, but which we consider to be free. Either of which would be really bad. Those would be, corruption.
Okay, and then we 2 questions. First, then we end with a block that is forever alien to us. It's every work on that block will require this 2 streams.
No, you could choose to write it. You could choose to write it directly to the journal block. That's fine too. Like you could have done it once. Okay. You could have included the block in the journal, right?
Yeah, but once we did it, it's everything will span, every write to this block will probably span two streams, right? Journal
no, the reason why we chose to do this in the first place is we're not going to do another write to it. If we thought it was going to be overwritten soon, we would have written it to the journal stream.
Okay, I understand.
Because that, if you think about it, if it's going to be overwritten frequently, you write it to the journal stream, because by the time you get around to cleaning that stream, you already rewrote it.
Okay.
So that block is already free. You don't have to do anything to it.
Okay, so maybe probably if there is a problem, I will need to garbage collect the block.
It's not a problem. We have to do it all the time. For every byte we write, we need to garbage collect 1 byte of some other stream.
Okay.
Right? Because we're writing sequentially. Yeah. So for every byte of free space we consume, we need to create a byte of free space, or else we're going to run out. Not necessarily in every write, but on average, for sure. Does that make sense?
Yeah, and what I was saying, if this block should be marked as only partially allocated, because
yeah, but we don't have to do that. We don't have to do that, because instead what we're going to do is when let's say we need to go through recovery, we had a power failure and we turn back on. We're going to go. We're going to check every stream on the entire disk. We're going to check whether they were sealed properly. That is, we got to the end, we wrote a checksum, and we closed it. And if not, we're going to walk backwards or forwards through the stream from the first record until we find an incomplete record. Then we'll close the stream with information indicating where it really ended, and then that's it. So that block that we wrote, it will be not in the allocation tree, so it's going to be free. It's no different from a block we wrote and then overwrote later.
Okay.
It's just not a block that, like when we go to GC that block, we'll just use it. We don't have to do anything.
1 second, I was signed out for some reason from the document.
No worries. That's sort of the core concept of this immutable block concept. You never go back and rewrite something once you've written it. So we have to maintain a secondary structure that tells us which blocks are allocated and which ones are free. So the fact that we wrote to the block does not mean that we can actually find it again. And we'll keep in-memory state saying that we did in fact write to this block, so future writes should be after it. But that's it. Like we don't have to remember anything else.
Okay, that makes sense.
Okay, so that's. We won't stop you. Yeah.
Well, no, you should stop me, because this is the core concept for the rest of it. Each one of these deltas is basically an atomic modification to a block. It's saying that, so it's worth, I guess, talking about how recovery works. So when we recover, first we scan each stream quickly, find all of the open ones. Then we figure out where the end of the most recent journal is. Then we rewind to the beginning of that journal. Then we replay the journal from there, right? And every time we encounter a delta, we first load the block it refers to and all of its parents into the cache, and then we apply the delta to that child, right? And so on until we get to the end of the journal.
Okay.
Assuming that algorithm works correctly, every block that was dirty when the crash happened should now be present in cache again, with the exception of anything that was only dirty in memory because we hadn't actually committed the write yet. And it should be atomically correct. We shouldn't have any partial transactions because we won't have read any partial records because they're checksummed.
So if the delta is very small for one block, so
I'm sorry, what's that?
So each delta is record a modification to a specific block, right?
Yeah.
So if the delta is very small, so how to align it properly?
So this is a pretty normal problem with like BlueStor's journal too. The fundamental thing is that with some of these drives, you simply can't do a write that's smaller than 4K. Period. So no matter what you do, if you want to write a thing that can be represented with only 1 byte of information, you got to spend 4K to do it. That's just one of the immutable laws of this kind of storage. The good news is it's not so bad. We can batch up multiple transactions into one transaction if we happen to have them available. So if the OSD is actually busy, we don't have to write out an empty record. We can write out one with several different transactions baked into it. Does that help?
Okay.
So we can't write out half a transaction, but we can definitely write out 2 transactions. And the deltas don't have to be aligned, I'm going to point out. The delta blocks have to be because we're not, we want to load them directly into memory, and it's inefficient to load unaligned stuff from NVMe. But deltas we have to decode, so we don't really care about that. The header delta, delta, delta part will be compactly represented. You won't get any padding until you get to the first block.
Okay.
But how to let garbage collector to clean the deltas if we want to?
So what's going to happen is the header has some basic information about what's in the record. This is per record, by the way. It knows how many deltas there are and what their offsets are. And it knows which blocks exist, what their offsets are, and what their types are. That is, it knows if it just has a little integer that says, am I a B-tree interior node? Am I an extent? Am I a block? Am I whatever, right? Then code can go look at the block itself and figure out what it needs to do with it. In general, however, we figure out whether a block is in use by using a secondary structure that I haven't introduced yet. Are we okay on just the basic layout and how hypothetically you could construct transactions out of it?
Okay, but let me for a second ask about reading. How does read work?
So let's say we're reading byte 256 of H object foo in pool 8, right? Mm-hmm. So that H object, if you've looked at the OSD code, translates to a 7-tuple that begins with a hash and a pool ID. So we traverse the H object tree from the root that we have in memory down until we get to the O node, which has the extent tree in it, right? We then traverse the extent tree until we get to offset 256, which should point to an actual on-disk block containing the data for that block. We then read the block. Some of this may be in cache, some of it won't be, some of it will, like any prefix of the tree will always be in cache. So if we have any block in cache, we have all of its parents in cache too. Not an uncommon design choice, honestly. So much of that traversal will be free, and then the rest of it turns into log n reads. As with any tree-based disk structure.
And we have the updated data in the cache. We don't need to go through the log to see the.
So there are a couple of choices we can make there, but for now, the design we're going to go with is pretty simple. Every dirty block is in cache. Whenever we do a journal checkpoint, we write out every dirty block.
Okay, and here we have a problem. We have larger size for a log, which is can write to disk compared to the cache that we have.
It's not necessarily a problem. You can you can always choose to write out a dirty block. It's no different from doing write back in any other file system. A little more expensive, a little less expensive, depends. Right? So let's say we have a dirty block and we're experiencing cache pressure. So we start at the, what do we do? We start at the leaf node and we begin writing out dirty nodes. Each time we write out a node, we of course dirty the parent, right? Because we have to change its location. But generally speaking, we'll write out in a breadth first, my bad. Whichever the one is the one where you do the leaves first. I want to say depth first, but whatever. We write out leaves before parents. That way, if we do that properly, we'll tend to amortize several updates per parent when we finally do the write-out. It sounds like a lot of write amplification, and it is, but the truth is every metadata technique involves a lot of write amplification if there isn't any spatial locality for the writes. You'll notice RocksDB is the same way. When you do a write for a sparse region of the key space, they all go into different level 0 caches, and then you have to read and write them and read and write them and read and write them to propagate them up the LSM tree. So that part's not an issue. So B trees are a little better, actually, because it's at least deterministic. Sorry, go ahead.
I have a probably more basic question. If you have cache pressure and you decided to write a block and all its pointers,
just
this block was
pointers.
Okay, yeah. But this block was referred to by the active log stream.
Yep, you just booted them. They're not relevant anymore.
How do you know that? How do you go over the?
You also recorded a delta in the allocation table saying it's gone. You wrote it out, right? So that means you logically moved it from its old location.
So all the delta blocks referred to specific block that is no longer there. This is what you're saying.
Yeah, eventually. So you'll go ahead and replay all of those deltas. Then you'll get to the journal event that moved the block, and then you'll forget them. That's it.
So the pointers in the stream are logical in that sense.
They're actually physical, but the thing is, they don't refer to things in disk. They simply refer to things in cache. So the first time you encounter a delta referring to a physical address you don't have in cache yet, you load it into cache. Then once you get to a delta that says, by the way, I deallocated this block, it goes out of cache, and that's it.
Okay.
You're right, though, that the delta stream does have to correctly represent that. Go ahead, Keith.
I'm not sure how you address the wandering effect. What I heard is that you mean that it's unavoidable, right? Every time you write a leaf note,
it's actively desirable. So wandering isn't a problem. So the truth is, for any tree structure, you have to do logarithmic extra work in order to update parent pointers, right? That's just always true.
I'm wondering if we can have a log or some way to alleviate this problem. Have a lookup table.
That's what this is. A log. So remember, we don't have to write out the parent block. All we have to do is write out a delta to it.
Okay.
We can delay write back for that block for a long time. Does that make sense? And the further up the tree you get, the further of those blocks there are. So writing them out at a journal checkpoint isn't necessarily very expensive.
So put it another way, if we wanted to add edit or modify a parent node, we just append a transaction, which change that parent node.
Exactly.
If the log is too long, or we are facing some pressure in the space or cache, we flush the node and apply all the logs to the
and then its parent gets a delta.
Yes.
Right. So hopefully at each level, if we have any locality at all, we actually capture several deltas every time we bother to do a write out.
Yeah.
That's the hope.
Until that node does not need to be split on anything. Okay.
And that's a real modification, right? That's an actual real thing. So when we do that, we get to do the same thing. We record a delta for, let's say we need to do a B tree split, works fine. The code that controls the B tree allocates 2 new blocks with the 2 split things and writes it to wherever. And then either as part of that transaction, it creates a transaction that writes out 2 new blocks representing the 2 new split pieces, and also a delta for the parent indicating or introducing the new pointer to the 2 new blocks. So you can handle splitting and merging through this mechanism as well.
We can design a machinery to represent this transaction in one delta or 2. Yeah. Okay,
precisely. So that's why I'm choosing to be really agnostic about how the deltas work. It means that as we write the tree structures that we use for our metadata lookups, we don't have to reinvent we don't have to write a whole new allocator each time. We can just use this one. And it's easy to combine all of the different transactions into one transaction. hopefully this will be easier to work with. I hope.
Okay. Me too.
Any other questions? Okay, so the rest of this is I'm not attached to. I'm just trying to work out which on-disk state I need to do garbage collection. But broadly speaking, there are metadata structures where there need to be in the stream. So we can figure out things like, so for the journal stream, since we only have one journal per CPU, we can just number them, right? Each journal epoch gets a number. And when we start writing out the next journal epoch, eventually we write a record in that stream that says, okay, this is the real new journal now. And that implicitly deallocates all previous journals. Which means that all we ever have to keep track of for a stream to find out whether its deltas are still relevant is the newest journal ID that has deltas in that stream. Because if we're on journal sequence 10 and we're looking at a stream that only has journal IDs up to 9, then we know that none of the deltas matter. And we don't even have to look at them. So all we care about in that stream are the blocks.
Is journal ID the same to the journal epoch?
I'm sorry, that's what I meant to say. That's a good question. I meant epoch. Yeah, so if we're looking at epoch 10, if we're on epoch 10 and we're looking at a stream with epoch 6, within that stream it has no deltas for a journal sequence above 6, then we know that none of those deltas matter. We only have to worry about garbage collecting blocks. By contrast, if we're looking at a stream with a journal that has deltas up to sequence ID 10, up to journal sequence 10, we shouldn't garbage collect that stream. We should find something else to garbage collect because the deltas in it are still relevant. We still need them for recovery. Okay, everyone on board with that, more or less, kind of? A little?
Okay.
I will also point out that just by nature, the beginning of every journal must contain the roots of the tree. So necessarily, there's a top of the tree, right? Which we'll get to in just a second. It's basically the address of the top O node, like the top of the O node tree and the top of the allocation tree. So we need something that references that from the beginning of the journal, because other than that, they're always in memory. They're fixed size. That's not really much.
The address of the root can change, right?
It can. So what happens is we will record special deltas that tell us where the roots are. But honestly, that's not even necessary. We don't ever have to move the root, if you think about it. If you think about it, because the root is necessarily very, very small, a delta to the root and the root itself are the same thing. So I think instead what we're going to do is we're going to mark like this header thing here. We'll have some metadata for each block, and there will be 2 block types that are special. Root blocks are special, and you have to look at them, whether they're in the allocation table or not, because they won't be. And allocation tree blocks you have to look at, because allocation tree blocks are not themselves in the allocation tree. But that's just a detail of how to bootstrap the garbage collector. So at a high level, if we look at the logical structure, so all of this is overlaid in what I described before. So the root is a single block, and it has physical references to the top of the O node tree and the top of the allocation tree. So the O node tree is a map from H object T to O node T. That is, it is a B tree where it's with leaf elements that are encoded O nodes. And the allocation tree is a tree with keys that are a tuple of a stream ID and a stream offset, which is to say a physical address. And it points, and the tree leaves are an allocation unit, or an allocation information D thing, which needs to have a few things in it, but the main thing it has in it is back pointers. And I'm not going to go into a lot of detail about that. What's important is that if you encounter, if you look in the allocation tree and find a physical address, the information recorded as back pointers is enough to find every block that points to it. So for a block, or like a data block for an object, it basically is just the object name and the offset. within that object, right? Because if you think about it, if you descend from the root, that's enough to find the block. Moreover, the allocation tree is conservative, or is consistent at all times. So if it's in the allocation tree, it really is referenced by the O node. And the flip of that is that any non-root, non-allocation tree block that is not in the allocation tree is free to be reused. And that's really important because if you remember before, I mentioned that every block, for every byte we write, we need to garbage collect 1 byte. But the hope, if we've done our jobs well and the workload has behaved, is that by the time we choose to clean a stream, that most of the blocks in the stream have already been replaced, right? Because we're mostly trying to clean streams that have short-lived data. For the most part, streams that have long-lived data, we're not going to want to touch. They generally will. They'll only become free very slowly. So we wouldn't touch those if we don't have to. So mostly, when everything is working well, we're garbage collecting streams where most of the blocks have already been replaced because they were overwritten or something, right? So for that reason, it's pretty important that it's cheap to skip a record. We don't want, so imagine if we didn't have the allocation tree and we just embedded a back pointer in the block itself. Then every time we wanted to like deallocate even a single block, we would have to retraverse the entire H-object tree to find the O node, then the extent tree to find the extent, to find, oh, duh, it's already been deallocated, right? So it's a bunch of CPU and read overhead to answer a question we were already pretty sure was false. So it's, in my opinion, probably worth maintaining a secondary structure, namely this allocation tree, that gives us an almost constant time ability to scan forward in a stream to find the next live block. Right? Because if it's listed in order of physical addresses, then we simply skip to the beginning of the stream in the allocation tree and then read 1 block at a time forward to find all the live ones. Then we do, in fact, have to do a traversal from the H object, but we only do it for objects we actually had to rewrite. And we wanted to load those nodes into memory anyway, because we're going to have to update them, right? Okay, so that was a lot of words. Does that make sense at a course level?
Yeah, I think so. I think it might be interesting to try to mark the logical structure with a heat map of what is expected to change in what is hot.
I was going to do that in the O node. I figure the O node will just track mutation recency, right? Because when we're traversing down to the O node, we have to load the O node, right? So we can load the most recent write time in the O node. That way, when we're doing the relocation, we'd have a pretty good sense of when the object was written and when it was last rewritten. But yeah, we can embed additional information in the allocation tree too. I'm open to all of that. In other words, both the allocation tree and the O node are relatively cheap to mutate, since we need to change them anyway when we're doing a write.
Okay.
Does that answer your question?
Well, it wasn't exactly my question, but it's a good answer.
Well, in other words, I'm saying you're very correct. One of the major linchpins to making this work well, especially with mixed workloads, where the OSD is serving both RBD and RGW, is the ability to identify whether an extent belongs to an old object or not. Because for rapidly updated RBD blocks, those we want to choose to put into the journal stream. But for any RGW block we encounter, for the most part, RGW workloads are write once, read never, right? So those objects never change and they live for a super long time. So when we do encounter one of those, when we're doing garbage collection, we want to make a point of putting it into a long-lived stream, one with other such objects. So you're completely right. That's pretty important.
So in that case, we
Okay,
need to use two streams for OMAP updates and object updates, right?
Not necessarily, no, because OMAP updates, so the transaction itself has to be in the journal stream. The question is, where do we write the object, the block we're moving? See, the transaction that moves the block has to go into the journal stream, or we have to do something really complicated.
But the block itself should go to another stream if it belongs to OMAP. Okay.
Precise. Well, no, sorry. When I say RGW objects, I mean the actual data objects.
Yeah, I mean the data, the key and value of the OMAP entry.
That part I'm not sure about. My guess is that those blocks actually change a lot. I think RGW buckets update really often. That's a good question, though. That's a tuning question we'll have to think about. And if we want to, we can also stamp these blocks as we write them with the timestamp we wrote them at. And then when we pull them back off disk, we can go, oh, okay, well, this is however many seconds old, right? So if we did want to make that happen, we could. That would allow us to detect like cold subtrees. So let's say someone's using RGW for timestamp data, and it happens to be the case that their object names are sorted by time. Then they only ever mutate the rightmost part of the B tree, if you think about it. And then they clean and then they deallocate behind. But depending on how long they keep those segments, you're right. Some of the internal and leaf elements of that B tree could wind up being really stable. In which case, yes, we would want to write those to another stream. But in the more common case, well, in a common case I hear about, it's pretty often the case that they're just writing like user-provided file names with no locality or properties of any kind, in which case the key space just kind of grows with keys inserted wherever the hell they want to. And in that case, the B tree as a whole actually mutates pretty quickly, and none of them would be stable. So both are possible.
Okay.
Okay, the Btrfs version of this is the backref tree, if you're interested. In fact, I'm going to link the paper in here after this meeting. I forgot to. It's a good paper. Or, well, it's an okay paper. It does an okay job of explaining the concerns anyway. Right. So, like I said, for GC, all we have to do really is maintain a pointer into the allocation tree for where we currently are for the next live block in the stream. And because root nodes, which includes allocation tree nodes themselves, do not appear in the allocation tree, we also have to actually look at each record as we go, just to check whether they have the root bit set. If they do have the root bit set, then we do have to look at the block and find out whether it's still linked. But that will only apply to the root itself, which will always be just a quick yes or no, depending on whether it's the current root or not. And then the allocation tree blocks, we need to check the allocation tree to see if it's still linked, because there's no other way to do it. But those are both very rare compared to the overall set of blocks in the file system, so I'm not overall concerned about it. And we could do things like mark a stream as never containing root blocks, in which case we could skip that check. That's an optimization we can do later. Okay. And we can do more exotic things I haven't thought of. This part is only like 4 days old, so if you guys have thoughts here, I'd really appreciate it. This GC part is really the Achilles heel of every log structured file system ever created. And we're making sort of one other change that systems usually don't do. I'm not really assuming the existence of asynchronous garbage collection. I am assuming that we will actually, in line with every client I/O, go do some amount of GC work. Which is not to say that we can't burst. Like, we could make it a sliding window where we create like a permissible set of ratios of use space to live space, and say if you're below this point, you must do work. And if you're above this point, you must not. Or other way, if you're below this point, wait, ratio of... If all use space is live, then there's no garbage collection work to do, unless you're out of space. And if you have like most of your use space is dead, you should do some garbage collection work. So we could create a range where it's like you're allowed to have up to 20% of dead data, provided you have the free space. And when we're not servicing transactions, we'll go ahead and do GC. But if you do have a consistent permanent client workload, then you'll quickly get to that 80% threshold, and every single client transaction will also have GC work mixed in. And that's the reason why I really wanted this sort of online GC structure, where all we have to do is maintain a very little bit of state about the allocation tree and the stream we're currently cleaning. And we can always squeeze in a little bit of extra work into each transaction that moves a block when we need to. Does that make sense to you guys? Both
I do. I think
how
so.
we're doing it and
Yes.
why?
Yes.
Cool.
Yes.
And I'm also really hoping that this will make it, like right now, we're having this problem with BlueStor where we don't have a good way of assigning a cost to a transaction because it's wholly dependent on BlueStor's internal state. Because we have no idea whether it's about to do a compaction or not. We don't know how much work it's built up. So this way should make it really easy to account that. We'll always know. So I spent a little bit of time down at the cost part, trying to sort of really fuzzily work out how much space we're wasting. Oh, some of this is wrong. We don't need the ID2 node part. This is really fuzzy, but I'll eliminate that because it's actually wrong.
Just a comment that not exactly for this moment, but it would be a good idea to think in advance what parts how we will use in this design PMEM. Which parts of this design?
That was the part I was going to get to next in this conversation. So the problem is most of this is really specific to how we lay out block devices. So unfortunately, I'm pretty sure that what happens is for a case where we're purely PMEM, we don't use any of this. For a case where we have some PMEM, my guess is this onode by object tree and this allocation tree both live in PMEM, and we write a completely different implementation for them. That just really exploits the PMEM to the most amount possible. So for that reason, if you look down at components, I plan on abstracting all of these things out. So like the allocation tree with this design, as outlined here, has a dependency on the stream manager stuff, but that doesn't have to be true if it's backed by PMEM. So in that case, you take this the allocator part and the onode part and possibly even the OMAP part, depending, and you would replace them with implementations that use PMEM instead. GC would still consume the allocator to figure out which blocks need to be cleaned, but it would never have to clean any of the metadata trees. It would only ever be cleaning actual data blocks. Yeah, I know it's fuzzy, but I hope that was enough answer for how we plan to evolve in that direction.
Okay, I think we should write it down.
Yeah, I just haven't gotten to that part yet. You'll notice the part at the bottom with the interfaces is completely empty. That's what I was going to do next. I was going to start actually writing code, well, at least interfaces, and start writing the stream manager component, and then develop a Gantt chart for which parts can be developed in parallel. But in other words, the brief answer to your question is nothing I've addressed here has anything to do with persistent memory. We will attack persistent memory by making sure we adopt a software layout where it's easy to plug in a replacement for the allocator, the OMAP, and anything else where that makes sense.
You don't see a design in which the whole log, for example, stream can be.
Oh, I'm sorry. Yes, the journal. You're correct. The journal would be another component that could live up there. Forgot to add a journal part. In other words, in that case, the ZNS wouldn't have any deltas. The journal would always write the deltas to. Yeah. So yes, I agree. You would probably write journal segments to the persistent memory.
Okay, thanks.
Yeah. I'm trying not to be too opinionated about that part yet, because the reality is once we start writing those interface components, we'll discover things. But you're right. I'll add a note here that's like, I wrote a lot for the block cache. All right. And the other thing is the cache, right? If the dirty blocks in cache are actually persistent, you don't really have to you don't have to write them back. You still have to journal, but yeah. Okay. Any other questions? I have like the cache is obviously very important for how this works. I was a little sketchy, but the goal clearly is for each core to have its own pool of memory and to allocate strictly out of that. And then we'll use some variant or just perhaps literally Mark Nelson's cache fairness system to ensure that, for instance, the O-node cache and the block cache and any additional caches we choose to create are able to share the same pool of memory fairly. We'll try to do that early rather than late, although I think I will not try to attack that first, because I think we can do some basic benchmarking before that point. Similarly, I'm going to leave OMAP until later because we could do basic benchmarking without it. So the initial goals will be to get the stream manager, the allocation trees, and the O-node part over to the extent tree written. Because I think the most torturous workload for this will be RBD. So I want to try to get right amplification numbers for that sooner rather than later. We can't run an OSD on it without OMAP, of course, but we can run benchmarks. Did anyone else have just radically different strategies they wanted to talk about? It's worth not rat-holing on or it's important not to get stuck on a single design too early in the process, and we are not late in the process. We can still choose a different design, though it would be good to voice it now. I will point out that none of this actually cares about B trees. This O-node by H object thing could easily be some other tree structure. The only thing it really cares about is that it's recursive, that it forms some kind of a directed graph.
And the fact that the amount of write amplification will be one of the two, probably one of the design decisions.
I'm sorry?
Whatever we choose for this, whatever design, whatever graph implementation we use here, will affect the amount of write amplification we'll have.
Sensitively, yes. That'll be one of the primary drivers. Yep, that's correct.
So we can play around later with this part to...
Yep, and like I said, I'm trying to, the goal is for these GC journal allocator OMAP, all of these components should be pluggable. So we can create more than one implementation of the way the OMAP works, as long as it respects some basic assumptions about how it interacts with the allocator. But I don't think those assumptions are particularly onerous, so I think it should be fine. That is, it's possible to express a backpointer, right?
Is the requirement of O-node tree and the allocation tree different? For example, the range search or
actually, they both actually do have to do range searches or range scans, as it turns out. The difference is that we know a lot about the key for the O-node tree. For instance, we know the first 48 bits will be the 64 bits will be the pool ID and the hash. So if we wanted to, the top elements of the tree would be really heavily optimized for the fact that they're numeric keys. We also know that the alphanumeric key that's next to the name of the object is well distributed among that space. So for the most part, we're only going to have one entry per hash. So for that reason, we're unlikely to have to do real string searches in the O-node tree. By contrast, in the OMAP tree, we really do have to do real string searches, so it will have to be optimized for that basis. Does that make sense? And we also don't want to waste a whole bunch of space repeating prefixes. So there are some B-tree tricks to avoid storing the full prefix of a key. I suspect that will be a worthwhile optimization because RGW bucket and items are often hierarchical. And so they'll often share like path components and such that we don't necessarily want to keep like copying around. But those are all details of how we implement the tree, and Ronan is correct. It has a large bearing on our write amplification and efficiency. And also, I want to point out, perhaps an even larger bearing on our CPU efficiency as we move these things on and off of disk and we construct deltas for them. So that'll be another concern. I'll also point out, I think I skipped this part earlier, deltas do not have to be byte range modifications to blocks. So the idea here is for every block to be typed. So when it gets read off disk, the cache will know what type it is. So when we're going to apply a delta, it's not just applying a delta to a byte range. It's for a B-tree block, applying a key insertion to a B-tree block. That will allow each of these sort of deltas to be implemented more efficiently than you could if it just had to be byte range modification. Just an aside.
And this is where you could plug in complex updates if we ever need, like those.
Hypothetically, yeah. I'm not as worried about that, but you're quite right. If we wanted to, within a single block anyway.
Yeah.
Or chain together. You
updating of counters or whatever.
Oh yeah, absolutely. That's definitely the case. For instance, if you wanted to update the leaf of a B tree that happened to contain O nodes, and your only purpose in life was to change the read recency, you could create a delta that just did that, right?
Yeah.
That just updated a fixed size counter at a known location in the block. Or rather, at a known offset from a known key in the block. That's what I meant to say.
Yeah, okay.
Or it could go all the way to decoding the O node, actually changing the counter, and then re-encoding the O node. You would have to know some things like it'll definitely still be small enough to fit in the B tree node, but yeah. Okay, so I'm going to start sort of working on this for the rest of the month. And I'll hopefully have something to report next week, although probably not a ton. I expect I'll have to spend some time.
What do you mean by working on, by improving this document, right?
No, I'm going to start writing the code. This is developed enough.
Are you going to write?
I'm going to start by writing this part, the stream layout. So there's a stream manager that needs to actually do writes, so I'm going to write that part. Then I'm going to start working on the cache, the in-memory component, because that's what interprets blocks off of disk. And by then, I should have had to make decisions about enough things that this document will be wrong, and I'll fix it. And then we'll move from there.
Okay. We're moving forward. Could you also update at least the interface, this document with the interface?
No, I'm absolutely going to do that. Yep. That's the purpose for starting now. If I make further guesses about the interface without actually starting to write code, the guesses will get less and less useful.
Okay. Could you also paste some useful links of materials?
Yes. I'm going to link particularly the paper to the Butterfs paper. If any of you guys want to, you all have edit permission. If you want to make comments, I strongly encourage you to do so. It'll be really helpful. And I think the discussion on the document will be helpful for everyone else as well.
Okay.
I mean, this again, much of this document is only like 4 days old, so it's totally possible you'll find a way to bypass one of these problems or make it simpler. Okay, yeah, I think that's it. Or that's all I've got.
Thanks, Sam. I still have some query regarding to the multiple stream, but I will update this document with my questions and my thoughts. Okay. Any questions? Okay. Have a good day. Have a night. See you next week.
Same for you. See you.
Thank you.
See you. Bye.
And for you, bye.